Hello, everybody. This is Dr. Dado presenting Advanced Probability Theory 2. Happy listening. Well, this is the second in the series. Here I intend to talk on most of the concepts that I've never mentioned in the elementary stage, as well as the first video. All right, let's go and see those prerequisites. Probability 1, 2, 3, sets 1, 2, 3. Reference material still remains these two. Random variables. Well, if these are two measurable spaces, a function x that maps event from this space to this space is said to be measurable. If whenever we look at its domain, there's a mirror image left in the first space. If it takes things to home 2, when the things it takes are from an event in home 1, then we say that that function is measurable. We have seen that this is a probability space, the triad. We saw that in the last video. But the function that takes home to a space of reals, actually intervals in the space of reals that are known as Borel sets, Borel sigma algebra, is also said to be a random variable as long as it's what? Numerically valued. Simply put, we say a random variable is any numerically valued function that is defined over a sample space. If there are two random variables, possibly defined on different probability spaces, we say that they are identically distributed or equal in distribution. If their distribution are the same, essentially the same, then if you supply an event to one and that same event to the other, they will be equal, they will give equal values. Then we see that, okay, it's just a play on variables. They are the same. We see they are identical in distribution or identically distributed. There are two probability measures and we give them the same interval, Borel interval, and they give the same values. We say that they are equal. Now, distribution function. Distribution functions are on Borel, measurable space, Borel. You are used to them as cumulative distribution function, the one we call CDF. The plot of the cumulative distribution function is called the OGIF, asymptotic to the line 1. Okay. That tells us a lot. From that OGIF, you can get anything you require about that distribution. Look at this instance. You can take it from the least point to a particular point. That gives you something. It means any point along the curve can be wholly determined. We'll see that later. So let's see the other properties. F is non-decreasing. That is why it's sometimes called a step function. All right. Limit to infinity is 1 because you go to the extreme. And if you are starting off, if you take the normal function, for instance, x is between minus infinity to positive infinity. When you are starting off, it is 0. The ogive, the tail of the ogive is 0, and it's asymptotic towards the line 1. Okay, so it's 1. The highest value it can reach is 1. Now, f is right continuous, meaning that the approach f plus is x being approached from above, and that's f of x. So these are the properties, functional properties. And when a distribution function exists, there's an underlying random variable. It doesn't exist vaguely. Okay. From that properties, it says if we are sure that f is entirely real and restricted to this interval 0, 1, then properties 1, 2, 3 are sufficient to define cumulative distribution function. The fact that we can stop anywhere along the ogive, x is any point along the ogive, enables us to have quantiles. Then essentially, what are quantiles? Quantiles are quartiles, deciles, percentiles. If, for instance, I had one example when I was discussing distribution in the video for probabilities 1, 2, 3. I think it's probability 3. And I was using the geometric distribution. I'm not too sure now. And I got the median. How did I get the median? I know along the ogive, the median occupies the 0.5 location. So I said, okay, integrate from the least point in the interval of definition to the point M, which will give you half. If you integrate to that point such that you have half, then that point is necessarily the median. You see? It means if I want the first decile, I won't equate it to 0.5. I would rather equate it to 0.1. If I want the 60th percentile, I will integrate it to 0.6. Like that, any point along the ogive can be uniquely identified. That goes further to give you this, that the quantiles, p quantiles are trapped between this. Then examples, indicator, random variable. This is just indicating whether omega here is involved with this event. If it's involved with the event, it will be 1. Otherwise, it will be 0, indicating whether it's involved with the event. Again, this is the continuous equivalent of the explanation I gave earlier. Actually, this was the one I used to handle the geometric case. Okay. Now, having said that, it doesn't end there. We say distributions. Then we'll be quick to say that distributions are either discrete or continuous. But essentially, researchers have shown that there are in existence mixture distributions. Well, some of these mixture distributions are even neither discrete or continuous. True, some of them can still be categorized. Now, what do we mean by mixture distribution? If these are CDFs, F1, F2, up to Fk, they are CDFs, and these are positive real numbers, such that they sum to 1, then a converse combination of them that has this law is known as the mixture of the FIs. So it's a mixture distribution. And there's an example here for you. You can read that this is a case of a system that is involved with two operations, and the distribution to each of the of both operations are different, and the weight is attached as to when in the processing the operations come into being. That's the example. These are the weights, and the weights are summing to be one. As such, this is a converse combination of these distributions. Now, what about location and scale mixtures? Actually, these are the ones that are responsible for location and scale parameters. For those that have been hearing that before, they help in changing the shape of the distribution. For instance, look at this distribution before. Now it has this shape. This is the discrete equivalent. Why here, which is used to perturb it, this used to change its shape, is known as scale parameter. Again, that's the law. This is the discrete equivalent. You might wonder at this point whether a mixture distribution is discrete or continuous. Yes, it can still be categorized. The extent depends on the distribution being mixed and the fixing distribution. For example, discrete location mixtures of discrete distribution are discrete in nature, and discrete location mixture of continuous distribution are still continuous in nature. Some advanced distributions that are neither discrete nor continuous. I said this is better explained with an example. And this example, this random variable xi is Poisson distributed with parameter lambda equals 3. That is discrete. Now, x2 is normal, standard normal. Then the convolution of both is linear, converse combination of both, given this law, what we have here. And at the end of the day, you find it that it is neither discrete nor continuous. Why is neither discrete nor continuous? This is the furthest I intend to go. I've ensured that I explain all concepts that you may find in papers in distribution. Most of the things, some distribution may have 2, 3 scale parameters, but you know what scale parameters are now. So once you know that, there's little or nothing you don't know about distribution, but distributions are continually being defined, being identified. So we still have some things to tell. Some things cannot be handled manually. So in my next video, by the grace of God, I want to include R and specialized packages on distribution. See you then. Bye for now. Thanks for listening. Please like, share, and subscribe. Thank you.